Today we're going to talk about Newton's laws and forces. Yesterday you did an activity where you took a look at motion and how to create position time graphs, how changes in position created velocity graphs, and how changing velocity would in fact result in acceleration. Acceleration, from what we learned yesterday, is a rate of change in velocity. What we also know is that there are three different ways to accelerate an object. The first way to accelerate an object is to speed it up. The second way to accelerate an object is to slow it down. And the third way to accelerate an object is to change its direction. And what we know is that when velocity and acceleration are parallel to each other and in the same direction, an object will speed up. When velocity and acceleration are parallel but in opposite directions, the object will slow down. When acceleration is in a completely different direction from velocity, we end up with a change in direction. Bottom line is, acceleration is how you change motion. Or it's not how you change motion, it's a change in motion. And acceleration is a change in motion. What we want to talk about today is how you actually change the motion. So how do we do that? We use a force. If we go to Google and we look up the definition of force, we end up with really, really terrible definitions. One of them is the strength or energy as an attribute of physical action or movement. This is a terrible thing to take another physical quantity like energy and use it to define a force. It's just, you don't use one physical quantity to define another physical quantity unless you know what all of them already mean. So this is terrible. The second definition is a coercion or compulsion, especially with the use of or threat of violence. That sounds really rapey, and that sounds like a really bad definition for force. If we go into the verb definitions, we basically get into the same quandaries, using other physical quantities to define a physical quantity that we already don't know, or something really violent. So forget that. We're not going to use that to define force. The physical definition of force is very simply a push or a pull on an object. That's all we're going to talk about it as, a push or a pull on an object. The symbol we use for it is a letter F for force, and the units that we're going to use in the International System of Units is newtons, and in the British engineering units, it's pounds. Fun fact, the United States is one of the only places in the world that uses British engineering units anymore. Everybody else is in the international system or metric. So, forces can cause accelerations. But what happens when all the forces balance on an object? If all the forces acting on you are balanced, can you accelerate? Can you move? Think about what you're doing right now. Probably sitting in a chair, watching this lecture, or standing around watching this lecture, and you do have forces acting on you. There is a pull dragging you down, bringing you into your seat. There's a push supporting you from the floor or your seat, wherever you're resting, so that you don't end up falling through to the center of the earth. You're not accelerating right now, odds are. I mean, unless you're driving in a car or something like that while you're doing this. The odds are you're not accelerating right now. So we've got forces. Forces are how we change motion. We have forces acting on us right now, but we aren't accelerating. Something really specific is happening here. The forces acting on us have balanced out. So, if we take a look at this animation, we see this guy jumping out of a helicopter. Seems crazy, but hey, he has a parachute. We're going to be okay. But as he's falling, you can see as you watch the animation, he does have an acceleration, a non-zero acceleration. But then this other force comes into play, this air resistance. And as that air resistance increases and eventually balances the weight, the acceleration gradually diminishes until it comes to zero. Now, picture somebody skydiving. When air resistance balances out with their weight, with their pull to the ground, do they stop moving through the air? No, they don't stop moving through the air. They continue moving. They're just not accelerating anymore. Now, if we continue with this animation, we see the parachute opens, we see a very large air resistance, which affects acceleration, and then eventually the forces balance out again. What's my point with all of this? When forces balance, you can't accelerate. You're always going to have forces acting on you. But when they balance each other out, then we can't change motion anymore. All we can do is maintain it. So that's Newton's first law. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion, unless acted upon by an outside force. Now, what does Newton mean by that when he says an outside force? He means an unbalanced force. So if your force is balanced, no acceleration. If your forces are unbalanced, though, we're going to see us speed up, slow down, or change direction. Newton's first law is often called the law of inertia. All right, and so we need to define inertia now, right? This is just a slideshow full of one more definition after the next. Inertia is officially an object's tendency to resist a change. So picture it. You're crossing the street, and there's a little kid on a bike barreling towards you. Are you freaked out about that? Are you worried for your life with that? Probably not, right? But now picture it, you're crossing the street, and there is a Mack truck barreling down the street at you. Maybe it's not barreling down the street. Maybe it's going as fast as the little kid on a bike. But are we going to get out of the way of this very large truck that's coming after us? Absolutely, we're going to get out of the way of the truck. What's the difference between the kid on the bike and the truck? Mass. One has significantly more mass than the other. And this is in fact the way we measure inertia, is by talking about its mass. Okay, so now if we tend to resist change, then if we're already moving, we will continue moving. And if we were already stopped, then we are going to want to stay stopped. So as we look at this animation, we see a ladder on top of a truck. The truck collides with the car in front of it. The car resists that change in motion. It doesn't want to move, but it ultimately ends up being forced to move. But the ladder continues going. Even as the truck slows down, the ladder continues going because it had inertia. It was in motion. It wasn't rigidly tethered to the truck, so it continued forward because it tends to resist change. So what's mass, right? We need to talk about mass. Mass is the amount of matter in an object, or the stuff that makes up an object, right? Volume is the space something takes up. Mass is the stuff that's in it. The symbol we use for mass is an M for mass. Brilliant. And the units we use for it are kilograms or slugs. Now, if you're looking at the slide, you're noticing a couple asterisks there. We need to take a moment to talk about mass, kilograms, pounds, slugs, and newtons. So, if you are from pretty much any place outside the United States, if somebody asks you for your weight, you're going to give something in the order of kilograms. Let's say you're a 60 kilogram person. You go to the doctor says, what's your mass or what's your weight? And you say, oh, I'm 60 kilograms. Okay. You haven't actually given your weight. You've given your mass, the amount of stuff that makes you up. It's a great unit because if you go to the moon, you're still 60 kilograms. If you go to a mountaintop, you're still 60 kilograms. But this is, in fact, your mass, not your weight. So now in the United States, we would give our actual weight. We would say, instead of 60 kilograms, we would say that we are 132 pounds, right? 132 pounds. That's a weight. That is a force, a pull of the earth on us. That's telling us how hard we're being pulled on by the earth. The conversion factor there, if you're good with math, is 2.2 pounds per kilogram. It is a conversion factor that only works on the earth. You can't go to the moon and use that same conversion factor. Because if I went to the moon, right, this is on the earth. But if I went to the moon instead, that n might be backwards, I'm writing backwards, I would still be 60 kilograms. But I would only be 22 pounds. Okay, so weight changes with how hard you're being pulled on. Mass is invariable. So now what is that word slugs on there? What in the world is that about? The unit of mass in British engineering is a slug. If you take your weight in pounds and you divide it by 32 feet per second, which is something we can talk about another time, you will actually get your mass in slugs. On the other hand, what is a newton? A newton is your weight, your pull, but in metric units. So if we take this 60 kilograms and we multiply it by 9.8, meters per second. Oh, that S is backwards, isn't it? Yes. Sorry. Per second. That will be your weight in newtons, which is going to be 588 newtons. So, why do I bring all of this up? Because we are coming to this from all over the world. And there are students here that have never used a newton to talk about force. And there are students here that have never used a pound to talk about force, and who in fact think that their kilograms are their weight, and it's in fact your mass. So I want you guys to kind of have this relationship when you hear these numbers go back and forth, right? It's a little bit more than 2 to get from kilograms to pounds on Earth. Mass is an invariable thing. It's the amount of stuff you're made out of, and your weight is a pull. 132 pounds is 588 newtons. It's the exact same pull. We're just using different size units to talk about it. That's it. So that's the difference between those units so that you're familiar with them. So does inertia matter? I would say yes, inertia absolutely matters. Why does it matter? It seems like it shouldn't, because it's just stuff. And if you're trying to move something side to side, then kind of the amount of stuff that's in it shouldn't matter, right? Except it does. So Dale Earnhardt, famous American race car driver, died in a crash. He was in a 5-point safety harness, much like what you see in a child safety seat. His car came to a stop. His torso was tethered to the car, so his body safely came to a stop. Unfortunately, his head was not, and so his head kept going because it had inertia. Literally, his skull came off of his spine, and that's how he died, because of inertia. So inertia actually does matter very much. What we know is that we cannot get inertia to change. An object will not change its motion if the forces balance. So what happens if the forces don't balance? That's where Newton's second law comes into play. Newton's second law is that the acceleration of an object is directly proportional to the net force acting on an object and inversely proportional to its mass. Great. I love it when they put equations in words. What in the world does that mean? That makes everything make physical sense when I take an equation and we put it in words. So let's break it down. What exactly does that mean? Acceleration is directly proportional to net force, the net force acting on an object. So what is net force? Net force is the overall addition of the forces. This is a Greek letter sigma. It means literally adding them up. We're adding these things up. And that means that if you have an object and it has some forces acting forward on it and other forces acting backwards on it, if we account for some of them as negative forces and others of them as positive forces, however you decide to define them, when we add them up, we will have the net overall force acting on an object. So acceleration is directly proportional to this. That means as one gets big, so does the other. Force is a push or a pull. So if you push something really hard, it'll get really fast. Whoa, way to go, Newton. That's really shocking, right? What's the second part of this? Acceleration is inversely proportional to the mass of an object. All right, well, this thing here, this guy right here, is a proportion. That doesn't seem to have changed. So how is it inversely proportional? What happens to this whole fraction as mass increases? The fraction decreases. So as mass goes up, acceleration goes down. So if you push something really hard, it'll get really fast. But if it's really heavy, not so fast. Didn't you kind of know that already? Right? So thanks a lot, Newton. First law, stuff that's sitting there is going to keep on sitting there until you move it. Second law, if you push it really hard, it'll get fast. But if it's heavy, not so fast. Sorry, everybody. It actually is insightful. Nobody else said it before Newton. So if we put these things together, then we have acceleration is equal to net force over mass. And that's Newton's second law. But physicists tend to be really bad at arithmetic, so we do a little bit of algebra on this, and we write it this way. Net force is equal to ma. I don't like writing it this way. The mathematician in me likes writing it this way because it's a simple equation. The physicist in me says, wait a minute, this is the resulting behavior. Acceleration is the result of the situation the object is in. Whatever situation the object is in determines its net force. The mass of the object is predetermined before we look at it. The acceleration is the resulting behavior. So these are two independent things that create a resulting behavior. Acceleration is dependent on the two. So now let's take a moment to take a look at this. Okay, so what do we have here? We have a cart with a fan on it. If I turn this on, you can hear the annoying sound it makes. It is running a fan. My daughter can tell you it makes a breeze since she's on the other side of the camera. We have a motion detector at the end here that's going to tell us where this object is located. And as we're already familiar with yesterday, we can go ahead and take a look at Logger Pro and actually see what's going to occur here. So I'm going to turn on the fan and then hit Logger Pro and watch the motion. Now, what we can see from this graph, shut that off while I talk about it. What we can see from this graph is there was a parabola in the position graph, so we are accelerating. There's a reasonably steady rate of change in the motion of the object. Now I'm going to add these two masses to it. And now we're going to see what this looks like. The first step I will do is I will store the last data, turn on the fan, and then let's take a look. Here we go. So you can see that the accelerations are definitely different. There are weeble wobbles in there, but for the most part, we can see that the acceleration has changed as we increase the mass. Now let's take an intermediate mass. Let's take one more and see what it looks like. I only have one mass sitting on here now. So at the end there, you can see that my hand touched it a little bit too soon and slowed it down. But through this central area, you can see that the accelerations of these objects are all distinctly different because of the masses that we used. So as you increase mass, acceleration decreases. Now let's take a look at if we increase the force. So this fan cart currently has 4 batteries in it. You can see 4 batteries sitting in there. I am going to take 2 of them out, effectively decreasing the amount of force that's in here. You might say to yourself, well, isn't that then going to make it so it doesn't run because I've disconnected the circuit? I happen to have 2 aluminum slugs that I can put in here that maintain the electrical connection, but actually allow it to run on less battery power. Okay, so now let's take a look at what we get if we have less battery power, so less force. And so you can see that it is running at a significantly lower acceleration with less force driving it forward. Let's add a little mass to it with the less force. And again, we can see that with less force and more mass, we have less acceleration. This is Newton's second law in a nutshell. So there are 4 fundamental forces that govern all of nature. They are the gravitational force, the electromagnetic force, the weak interaction or the weak nuclear interaction, and the strong nuclear interaction. Some of these we are already very familiar with. We're very familiar with gravity acting on these infinite cosmic scales, but in fact, in terms of strength, the gravitational force is actually the weakest of the 4 fundamental forces. Electromagnetism is pretty much responsible for more than half of all the stuff that matters to us, right? We really love our electronics, and that's all electromagnetic force. Your parents stick your artwork up on the fridge, that's magnetism. The weak interaction, it acts on a nuclear level, so you don't really see it as often in your daily life, but in fact, it is responsible for nuclear decay. And then the strong nuclear force is actually what binds all matter together. So it's actually a ridiculously strong force. Unfortunately, it acts over a ridiculously tiny distance, not even half the diameter of the nucleus of the atom. So it turns out that the strong nuclear force is like Aladdin's genie, right? Infinite cosmic power, itty bitty living space. And the gravitational force, while we're familiar with it for breaking our bones and things like that, it's actually a very weak force, but acts over huge distances and is responsible for our solar system orbiting the center of the Milky Way. It was once believed by scientists, it's still believed by scientists, that these four fundamental forces acted as one super force at the beginning of the universe, at the Big Bang. And that as the universe cooled, those forces began to splinter off into different behaviors that we now call these four forces. Science is working right now with experiments like the Atlas Accelerator at CERN to try to experiment and actually unify these four forces. Right now we've gotten to unifying three of them, but gravity is just this elusive, doesn't want to fit in with everybody else's force, even though mathematically it looks similar. So, this is what governs all of nature, but that makes it really difficult to talk about, like, oh man, I've gained so much weight. Like, what are we talking about when we talk about those types of forces? So we need to have some kind of common language to talk about what we deal with on an everyday basis. So first there's weight. We talk about weight, and that's actually the gravitational force. That's a fundamental force. It's an attraction between massive objects. So literally, I am attracted to the Earth, and that's what gives me my weight, and that's what gives you your weight. It's calculated by taking your mass times the acceleration of gravity on whatever massive object you're on. And it typically pulls, we talk about it pulling down, but it pulls towards the center of the axis that connects, it pulls along the axis that connects the two masses, but typically towards the center of the more massive object. Normal force is a support force. It's perpendicular to the surface. It comes from the surface that you are on. And we call it normal force, but it's actually a special case of the electromagnetic force. So you have a whole bunch of electrons on your bottom, and the chair you're sitting on has a whole bunch of electrons surrounding it, and they actually repel each other. And that's what creates that support that holds you up and keeps you from falling through your chair or falling through to the center of the Earth. So we can do a whole bunch of calculus over the surface of an object and calculate all the stuff that we need to calculate for every one of those electrons. Or we could just call it normal force, and that's actually a lot easier to work with. It always acts perpendicular to the surface. So fun fact, when we talk about the unit circle, right? That was a terrible circle. We know what a tangent line is, right? A tangent acts and intersects at only one point in the circle, but there's actually something called a normal line, and that normal line is perpendicular to the tangent line. And so that's actually why it's called a normal force, because it's consistently perpendicular to the surface. Normal force very often balances your weight, like in the case that you see here, but it doesn't have to. Normal force is actually what your scale is reading for you. When you step on a scale, it pushes back. The scale tells you what it's pushing back. It doesn't tell you your weight. So if you have a bathroom scale at home, go take it on a hill in your yard, or just balance it on some kind of an incline and stand on it. See if it still reads your actual weight, or if it reads something less than that. Then there's friction, another special case of the electromagnetic force. Again, objects are surrounded by electrons. As one object moves across the other, those electrons move across each other, and they resist each other, right? Electromagnetic repulsion. We could do a bunch of calculus there, or we could call it friction and move on with our day. It's a force that opposes the relative motion between two objects. It's calculated based upon normal force. There's a mu there that's called a coefficient of friction. It's a property, basically the measure of roughness between two surfaces, and it's unique to every two surfaces. So your shoes against the ground are going to be different from your shoes against asphalt, or your shoes against ice, or against a rock on ice. You know, depending on the two surfaces, that relative roughness is different. We can talk for ages about the coefficient of friction, but what you need to know for right now is that it is basically a measure of roughness between two surfaces. So if I take a look at this object, it's about to slide down an incline. Gravity is pulling down on it. Normal force is supporting it perpendicular to its surface. Friction is resisting its progress down the incline. So friction, again, could be a special case of the electromagnetic force, or we just call it friction, move on with our day. The more we increase the normal force, the higher the frictional force will be. I think that's all I want to tell you about frictional force. Applied forces are forces from one object onto another. So that is me grabbing my kid by the ear and dragging them back into the house when it's time for bed. I don't actually do that. I'm not really a fan of abusing my children. But that is a force from one object onto another. We could call it an electromagnetic force because, again, all the electrons in my hand are repelling all the electrons in this and pushing this object out of the way. Or I could just call it applied force. Applied force will be in the direction of the pull. So in this case, this is a person dragging an object along. So this is perhaps this kind of a situation where we've got the weight pulling on the object, we've got a normal force supporting it, but then we've got a person here that is dragging this thing along with all their might. Remember that you're supposed to be riding backwards. And so they are dragging this rope on us, trying to drag this thing along, and the end result is that there's an applied force along the direction of that, which leads me to, since there's a rope, it leads me to tension, which is a force in a rope or a chain. Tension always acts along the direction of that rope or chain. And again, we could call this an electromagnetic force because what is a rope, in fact, but a whole bunch of fibers that are interlocking, and those are their electrons that are making them interlock, or I could just call it tension. So these are a bunch of the common ones that we will talk about that you will run into when you're trying to talk about the behavior of an object. You will see tensions, frictions, applied forces, normal forces, and rather than doing that crazy calculus, we'd like to have this kind of common language for us to work off of so that we know what forces we're talking about without just calling everything electromagnetic force. All right, so the next important thing, if you noticed in all of those definitions, forces come in pairs. That whole Star Wars bit, that the force is strong with this one, it makes no sense. All right, forces are not held within you, they interact between you. Forces act between two objects. They are, in fact, interactions. So if we look at this person running off of this canoe, we notice that as they run forward, the canoe is pushed back. Because as the person pushes back on the canoe pushes forward on the person. And then the resulting motion is that the person gets to move forward, but the boat moves back. So it's important to always think about forces as interactions. With that is Newton's third law, and this is where he actually gets really, really insightful, where he says that every action has an equal and opposite reaction. This is a big deal. In boxing, if you watch bare-fisted boxing, not only will somebody's face be bloodied, but the other player's knuckles will be bloodied. Why is that? Because yes, one person punched the other guy in the face, but that person's face punched that guy's knuckles, right? So I got into a car accident once, and my dad said to me, wow, that car really walloped the heck out of you. And I said to him, well, I walloped the heck out of it too. So why is it then that my car was totaled and their car drove home, just their fender fell off? Well, we're back to inertia. This was my car, and this was their car. It was like a big old Ford Expedition, gigantic American-style SUV. They had a ton of mass, and I had not a whole lot of mass. So we hit each other with equal and opposite forces. But who had the greater acceleration? If I had a little bit of mass, I had a lot of acceleration. They had a lot of mass, so they had only a tiny acceleration. And that resulted in an equal force between us. So, Newton's third law is that forces are equal and opposite to each other. The moon orbits us, we orbit the moon. Wait, that's not right. The forces are equal. The moon orbits us because it accelerates more. So, need further proof about Newton's third law? Let me bring my assistants in. Hey, go. So this is Lucas.
Hello.
He has a scale. I need you to hold that scale, please, young man. Have we talked about what we're going to do?
No.
No. This is Teddy. He has a similar scale. Can you hold it up? Maybe the other way. There you go. All right, now I'm going to hook these together.
Okay. Here you go.
You have to hold it, though, dude.
Oh, yeah. Okay.
Right. Great demo. And you need
This
to
is
hold
working
yours.
out perfectly.
Ready? Now, Lucas, can you please pull on yours? Teddy, don't you pull. You just hold it.
Okay.
You just hold it, and Lucas, you pull.
Hey, look, it's moving.
It is moving. Now pull a little harder. Now pull a little harder. Oh, and Teddy even let go. And do you see that they're reading the same number, everybody?
Yes.
Pretty
Right?
much,
Even the
yeah.
boys can see that in the reflection. Right? No matter how hard Lucas pulls, Teddy and I pull the same way back every time. And that's Newton's third law in a nutshell. Thank you, boys. You did a great job.
You're
You guys
welcome,
can go
Mommy.
off that way. To summarize Newton's three laws, Newton's first law, nothing changes unless you force it to. Newton's second law, the harder you push, the faster things will change. But the more inertia there is, the tougher it's going to be to make that change. And the third law, when you make a change, expect pushback. So that is everything for Newton's laws. I hope that will help you going into your lab later on today, where you're actually going to get the opportunity to take a look at Newton's three laws in real time. Thanks very much. Okay. So, I've already forgotten what I was going to say.
4 fundamental forces.
Right. So therefore,
Record. Okay. We're recording in Zoom.
thank you. Okay, don't beat me up. All right. So,
Now go upstairs.
to summarize it,